Good morning, everyone. I'm so excited to tell you the story that me and my co-authors have been working on, pairing geomorphology and paleoclimate to learn a little bit more about how the Central Appalachian landscape changed in response to climate change at the end of the last glaciation. As the speakers before me explained, permafrost was extensive at mid-latitudes at the last glacial maximum and at previous glaciations, including in central Appalachia, where we have geomorphic and cosmogenic nuclide evidence of not only extensive periglacial erosion at the most recent glacial maximum, but also at previous glaciations. The only problem is these two techniques integrate a lot of time, such that we can't really zoom into what these deglacial periods look like, and in particular, what temperature and moisture conditions promote the formation of some of these landforms and deposits. And so I'm looking to look at shorter millennial or even centennial timescales connecting climate to geomorphology. If we develop this mechanistic understanding of permafrost geomorphology, we can not only compare and contrast postglacial Appalachia to the postglacial Arctic or other areas that have legacies of permafrost processes, but we can also make better predictions for how high latitudes are going to respond to anthropogenic warming and wetting. Palynologists in the past have reconstructed Appalachia's paleoclimates using pollen records, but relatively little attention was paid to the sediments and the stratigraphy of these records, where in fact if you look at the sedimentology, you can see that the deposits change with a changing ecosystem and therefore perhaps climate change, implying that these sedimentary records preserve some kind of climate erosion link, if only we could interpret sedimentary processes with climate conditions. I decided to test this idea at Bare Meadows Bog, where folks in the 50s and 60s had taken pollen cores and had found a switch between cold and warm climate vegetation assemblages. And the peat sediment interface at this site had been dated to about 10,500 years ago. So there was some indication that there would be a siliciclastic record of this transition from cold to warm after the glaciation. So we collected new data sets here, including ground penetrating radar and auger samples of the peat sediment interface, as well as digging into the sediments under the peat. To connect geomorphology to climate change, I'm going to attempt to constrain the timing of different hill slope processes using the different types of deposits to infer different surface processes, as well as their timing with radiometric dates. And then connecting those surface processes with ecosystem and climate states by using our pollen records and water level records in the bog and organic material. So the two main methods I'm going to use to tackle this is looking at the spatial distribution of facies and characterizing the sediments found in those facies by using coring, ground penetrating radar, as well as core scanning to get at bulk geochemistry and other attributes of the sediment. In addition, we're going to construct the vegetation and ecosystem history at this site by using new dates and pollen counts, connecting them to existing historical records to do a new absolute dating chronology at this site. In this sketch representing the observations we made in our transect from the edge of the bog to the middle of the bog, we took from sediment cores and ground penetrating radar. What you see is that at the edge of the bog, you have these coarse bouldery deposits, which we're inferring to be continuations of the solifluction lobes found on the hill slopes. But as you move in towards the bog, you start to encounter a blue-gray silty clay and no more boulders. Dating plant macrofossils, we found that the peat sediment interface dates to the early Holocene, whereas the sedimentary deposits had been accumulating since about 15,000 years ago. One important outcome geomorphically from our dating was that the matrix of the coarse solifluction lobe was dated to 13.9 thousand years ago, which is during the warm Bowling-Aileron period. So we infer that solifluction was active during this warm period. The other interesting fact is that the peat sediment interface rose rapidly over 2 meters over the course of 1,000 years from about 10 to 9,000 years ago, and we found a layer of woody debris in between the sediment and the disaggregated peat, from which we infer that there was a rapid water level rise from 10 to 9,000 years ago. By conducting pollen counts on intervals that we radiocarbon dated, we can correlate our pollen counts to the counts performed in the 60s so that we can basically scale existing pollen records with absolute dates, allowing us to see what was happening at Bare Meadows in the context of global climate change. So in these next slides, my radiocarbon dates, where I have constraints, are shown at the bottom as red arrows, and everything's put in context of the oxygen 18 isotope data from Greenland ice cores. And you can see how the ecology at this site changed in the context of global climate events. Two things in particular caught my eye. First was the ecological turnover that occurred at about 9,000 years ago, where the pine parkland was replaced by alder, with a pecan alder there, that is then followed by oak and other deciduous trees. And then as well as the grasses that peak in Poaceae true grasses popping out at the Bulling Alarod, and the dominance of grasses over sedge and sphagnum at that time leads us to interpret that it was a dry period during that warm period. We can also now quantify the rate at which peat was accumulating in the depot center from that 1965 core, and in particular, the rapid rate of peat accumulation between 10 and 9,000 years ago coincides with that theorized rapid level of water level rise from the peat sediment interfaces and the drowned woody layer that I talked about previously. We scanned one of our cores, this SO2 core, every 2 centimeters using a core scanner that, among other things, measured bulk geochemistry. So I'm showing the results of the core scanning in a principal component analysis, where I've color-coded the cored intervals based on the facies I observed in the core, and I've also added points from the hill slope, both from the soils as well as the bedrock from a core that we took up on the nearby hill slopes. It's really clear that PC1, which explains 2/3 of our data, is just a function of more and less organic material in those intervals. But PC2 was a little less clear, but it became more obvious when we added the data points from the hill slope, which showed that the bedrock and soil compositions were really stratified on that second axis. What this means for our data is that we're interpreting a more local versus non-local signature in the elemental composition of the core, and that depending on the facies, that unit has more or less local bedrock or more or less non-local material. And one of our hypotheses is that the non-local material is dust that is blowing around in this post-glacial landscape. So now we have this temporal view into the evolution of the composition of those sediments, which you can see as these curves of PC1 and PC2. And in particular, I've compared it to the record of Greenland dust flux, which seems to correspond really nicely with that PC2, that black curve, which we hypothesized to be a balance of more and less local sediment input versus something like dust. And it seems to really correspond to when dust flux was higher and lower in Greenland. Though there is this tricky part here where geochemically the sediments that are accumulating on the edge of the bog look like dust, but the dust flux is low from Greenland. So we have to figure out what this means. And the way that I'm interpreting this trend is that combined with all of these independent lines of evidence that we have of rapid water level rise, high turnover on the hill slopes, what seems to be sort of the turning on of the hydrologic cycle. My argument here is that we're really turning on slope wash and washing of material from the hill slopes into the bog, and that geochemically started to look like the dust that had settled on the hill slope and then turned into more looking like the local hill slope sediments. So really what this is a signature of is slope wash and erosion of material from the hill slopes, as opposed to sedimentation prior in the core, which was more of a function of dust inputs, so non-local, non-hill slope processes. And so a summary of my time series data in cartoon form would be starting off dry and sort of warm, but mostly dry in the Bowling Alarod with a low productivity and solifluction dominated landscape that turns into one that's a little more productive, a little warmer and a little wetter, but stable up until after the Younger Dryas, after which point you turn the hydrology back on, you destabilize the hill slopes, you start to erode and slope wash and deposit lots of sediment into the basin there, but you're also rapidly accumulating peat in the depot center. You've got ecological turnover on the hill slopes with alder replacing pine, and then finally you actually stabilize the water level because you start draining at the outlet, and at which point your hill slopes stabilize and your oak forests take over after that. So I found it really satisfying that we got to use geomorphic and paleoecology tools in order to tell a story about how this landscape changed in response to changing climate. We learned about how temperature and moisture are really important drivers of geomorphic change here. And we also learned about ecology following geomorphic change in this landscape, which is interesting to me because in the modern Arctic, it's sort of a chicken and the egg problem, whether or not vegetation change is responding to geomorphic change or vice versa. So I thought that was an interesting takeaway as well. We also really quantified the importance that dust plays not only in forming soils in central Appalachian sandstone areas, but also that it is an important geomorphic agent in these landscapes. And so as part of future work, I want to collect more of these paired paleoclimate, paleoerosion records from existing pollen records throughout central Appalachia. And that's the work that is in part being supported by the QGG Marie Morisawa Award. And so I'm really grateful for that support and excited to continue this work. Thanks so much.